Now, we talked about the broad sphere last time, and let me remind you what it is again quickly. So now we have this embedded system, right? We said that we have a qubit, and in the past, we say that a qubit it is like four degrees of freedom, right? You can have psi plus out, sorry, psi, right? Maybe I should just write here. Psi equals to alpha 0 plus beta 1, right? And of course, alpha and 0 are complex number. And then we say that we don't care about the global phase. And then we say that we don't care about we also say that it has to be normalized to unity. And that's why it becomes 2 degrees of freedom, that you only need two parameters to describe it. One is theta and other is phi. Okay, now, which is good, right? Then because of this, we map it into our 3D space, and that's why we say we embed the C2 space. This is the C2 space in our real 3D space. And with this, then we have some meaning for the XYZ, because after all, the complex space is not in our real 3D space. There should be no meaning for XYZ, right? But now we have this. Sorry, I need to meet people. Okay. So today I want to talk about, last time we talked about the expectation value, and now I would like to talk about the rotation. So what is the meaning of rotation? Let me give you the definition, the equation first, and then we gradually try to understand what it means. So first, let me just tell you the rotation matrix is given by this Rn gamma, which is a number, equals to exponential negative I divided by 2 n dot sigma gamma. A very complicated equation, right? Looks like very complicated. But however, this is not really that complicated if we look at it clearly. But first of all, why do we care about rotation? That is a very important thing. Why we care about rotation? Because as we said, the so-called quantum gate or one qubit gate is nothing but try to rotate a state on the broad sphere from one point to another point. Any quantum gate, any one qubit gate, perform a rotation. And that's why naturally we will ask, if I want to go from one point, for example, 0 to plus, how should I rotate it, right? So that's why rotation matrix is very important. And last time we mentioned that any rotation can be decomposed into 3 rotations, right? For example, can rotate for an angle about z-axis, and then rotate about the other angle of let's say y-axis, and then rotate about z-axis again, right? And so that is great, right? But then what is the general rotation matrix? Instead of rotating about this xyz, what if it's another particular direction? So now this direction has some important meaning, because this direction is really related to the 3D space, right? Because we embedded it in 3D space. And this direction is given by n. So what we're actually doing now is we're saying that n is a unit vector, right? N equals to nx, ny, nc. N is equal to nx, ny, nc. We talked about this last time, right? But what is sigma? Sigma is the Pauli vector. Some problem. What is the Pauli vector? It is sigma x, sigma y, sigma z, right? So we do have this term here that we learned last time. Remember? So this one, last time we learned about this, right? And so what is this? If you try to find it, n dot sigma is again, this is just has the 3D basis, right? So what it means here is I have so much of x hat, so much of y hat, so much of z hat. This one I have so much of x hat, so much of y hat, and so much of z hat. So their inner product is just the multiplication of the corresponding coefficient, right? So last time we say, okay, this is just nx times sigma x plus ny times sigma y plus nz times sigma z. And it is just a matrix which is given by nz, nx minus I ny, nx plus I ny, and then negative nc. Remember? And last time I had a typo, I put plus and plus 1 and negative 1, and one of you pointed out my mistake, right? Because this part is because of the z, sigma z is 1 negative 1 times z. Okay, so this is what we have, right? So it is given that if you say, ask about how much rotation we have, it is kind of, this is telling us that the rotation about n hat by gamma degree, okay, is given by this equation. Rn gamma, which is equals to exponential negative I divided by 2 gamma, and then nc, nx minus I ny, nx plus I ny, negative nz. So what I've done is just that I substitute n dot sigma by this matrix. And the reason we get, the way we get this matrix was by nx times sigma x, which is 0, 1, 1, 0, right? That's why you have nx here. And ny here, you have negative I times ny, I times ny. That's why you have this off diagonal term, and then you have this diagonal term, right? I just substitute this here. So this is given, we did not prove it, but let's just take it for granted. So if you want to know the rotation of a matrix, right? The rotation on the broad sphere about a given direction, that is the rotation axis, right? By gamma degree, then it is this matrix. Okay. Any questions so far? I did not prove it, right? I just give you the matrix and we just take it for granted. Now, if no questions, let's just look at some special cases, okay? So that we can understand better. For example, what if n hat equals to z hat? What does it mean? What is the meaning of n hat equal to z hat? It means that you are rotating about z, right? Because now this is the axis you're trying to rotate about, and this is n hat equal to z hat. That's the first thing. Okay, and what if gamma equal to pi? What does it mean? It means we want to rotate about z hat by pi, right? So if you look back here, it's just saying that no matter where you are, we're trying to rotate about this z axis by pi, by 180 degrees. That is the meaning, right? So based on that, right, can you tell me what is nx in this case? One no? Maybe I can remind you. N hat equal to nx, ny, and z. And now it is just equal to z hat, right? What is, just remind you, this means nx hat, nxx hat plus ny y hat plus nz z hat, right? So I just say that n equal to z hat. So then what should be this matrix look like? This vector look like? Nx should be?
0, 0, 1.
Thank you. Very good. 0, 0, 1, right? So that is what we have. And then gamma equal to pi, right? So now I can construct the matrix. So Rn, just the general form, right? Rotation about n for gamma. Now it is rotation about z hat for pi. Then I plug in the equation. Let me remind you what it is. Because x, n, x, and y are 0, right? So these two are 0, the off-diagonal term. And then nz is 1, right? So this is 1, negative 1. And then times negative I divided by 2 gamma. So this is very easy. Just exponential negative I divided by 2 gamma times 1, 0, 0, negative 1. Now, for some of you might feel very confusing. What is the exponential of a matrix? This is a matrix. I will cover it in the next slide, okay? Now we just take it for granted again. You just agree that we can exponentiate and make a matrix. But more importantly, because I will tell you later, but now we just take it for granted, because it is diagonal. The matrix is diagonal. So when we do exponentiation, this is just equals to exponentiating individual element. Okay, so we have 1, right? So it's exponential negative I divided by 2 pi. And this is 0, 0. We only exponentiate the diagonal, okay? The off-diagonal term will be 0. I will prove it to you that is correct. But now you just trust me. So another term is going to be I divided by 2 pi. Okay, are you okay? Because this is diagonal. When I exponentiate this matrix, or you can think of this is just a number. This number go into 1, right? This number go into negative 1. So I will get negative I gamma 2. Well, gamma is pi, right? So it's I negative I pi divided by 2. Here is negative 1, so it's I divided by 2 pi. This one just go in. And then you just have a matrix, right? But because it's diagonal, the result is just that you exponentiate this diagonal matrix. So it's exponential of this one and this one. Okay? This is important. Any questions? You can do this whenever you see a diagonal matrix. If no, then we will continue the evaluation, right? So what is exponential negative I divided by 2? This is just cosine pi divided by 2 minus I sine pi divided by 2, right? So this term, because it's pi divided by 2, cosine pi divided by 2 is 0. So the other is just negative I, 0, 0. Okay. And then the lower right term, now it is positive. So everything is the same except this will be I. Make sense? Take a look if you have any questions. So this matrix will rotate your qubit by pi about the z-axis on broad sphere. Okay, now let's try to do something and we will recognize something very interesting. So I rotate about z by pi. I apply this to the plus vector. I just take one of them as an example. Right? This is an example. Apply this to plus. Right? So let's do that. The matrix is negative I, 0, 0, I. And what is plus? 1 over square root 2, 1, 1, right? So let me apply to it. 1 over square root comes out. Okay? And then I will get negative I and I. Because this is negative I times 1 plus 0 times 1, negative I. 0 times 1 plus I times 1, I, right? So let me just factorize it. So I want to get something more easier to see. It's negative I divided by square root 2. I factorize negative I out. So this is 1 negative 1. So what is 1 negative 1? It is just negative I minus, right? Correct? Because 1 negative 1 divided by square root 2 is minus. So this is negative I minus. Let's take a look. Go back to the broad sphere. The broad sphere, I say I rotate about z axis by pi. Am I right? It becomes negative, becomes minus, right? So this is correct. But it doesn't become minus itself. It becomes negative I minus. Is this okay? Is there any problem for me to get this result? It is okay, right? Because this is the same as minus by a global phase of negative I, right? So we already said that in order to map this to broad sphere, we actually sacrifice the global phase, which is not important physically. So when I say when you rotate from plus to minus, it actually does not give you minus. It gives you minus I minus, which is correct. This is the exact solution. However, for every point on the broad sphere, it actually represents infinite number of states. But these states only differ by a global phase. Also, there's no contradiction. But here, point out one very important thing. Which state will you end up at? Actually cannot be observed from broad sphere itself because the broad sphere is kind of degenerate, right? One point represents many number or many states, although the states only differ by a global phase. Okay, so I hope that you will understand this is exact. I do go to negative I minus, but it is correct. And even on broad sphere, it's still correct because we will not compare the global phase. Okay, any questions?
In front of the I, is that considered a phase?
Yes, the whole thing minus I is a phase. So we can study a little bit more, right? So what is minus I? The whole thing is a phase. So minus I, you can see is just equals to cosine negative pi over 2 plus I sine minus pi over 2, right? It turned out that we just done this earlier, right? So negative cosine pi over 2, which is cosine pi over 2. So I sine pi, negative pi over 2, which is negative I sine pi over 2, right? We just say that this is just equal to exponential negative I pi over 2. So the global phase is actually negative pi over 2, right? So this is the phase, right? Sometimes when we say the phase, we only refer to the angle. Sometimes we just say it lousy as e to the power I angle. It is okay, right? So they have a phase difference of negative pi over 2. Okay, if you don't have this negative, then the phase difference is pi over 2 because this will become positive. You find that this is equal to I is just exponential pi, I pi over 2. Right? Great. Any other questions? Now, if no, let's continue to rotate one more time. So what I'm trying to say is that instead of rotating plus by pi, can I rotate it by 2 pi? Of course. Rotate pi first and then rotate by 2 pi, right? So that's very natural. So I will negative I, 0, 0, I. This is the rotation matrix. But this time I will apply it to negative I divided square root 2, 1, negative 1. Because this is the one after pi rotation, right? So this is this one. So now I apply one more, then it will be this one times this one, right? So let's play with that. This is negative I divided by square root 2. I just take this out and then start doing the math. The matrix multiplication is going to give me negative I and negative I. Because negative I times 1 plus 0 times negative 1 is negative I. 0 times 1, I times negative 1 is negative I, right? So I'm going to factorize this out. Negative and negative is gone. But I times I is what? Is also negative. So it is negative 1 over square root 2 plus, 1 over square root 2, 1, 1, which is equal to negative plus. Okay, first of all, that is strange. I rotate by 360 degrees. I actually don't go back to plus. I got negative plus. Now, first of all, is this wrong? It is not again. From Bloch sphere, I rotate by pi, it go to minus. By another pi, it go to plus. But Bloch sphere does not tell us the phase because it's the generator in that sense, right? The full mathematics tells us that you don't go back to your original state by rotating 360 degrees. You go to negative plus. Now, there is not a big, you should not feel this is a big problem because after all, this is just the state embedded to the real 3D space. In our real 3D space, if I rotate by 360 degrees, I should go back to my original state. But again, every point here represents many states, and there's their difference by a phase. So here, this plus and this plus are not the same. They're different by a phase which is negative 1. Turn out to be pi, right? Cosine pi is negative 1. E to the power I pi will give you negative 1, right? So from this sense, it's not really a problem, right? But there's something deeper. This is related, even related to topology. Today I cannot demonstrate, but you will see that in some system, in the real space, you need to rotate by 720 degrees in order to go back to original state. Okay, so that's why this is allowed. Okay, so because they are in two different space, this is like the Morbius ring. I don't know if I pronounce it right. Anyone can correct me. Instead, you have this ring, right? You have a ring like this, right? So if you go by 360 degrees, you go back to your original position. But if you have a ring like this, I hope that I can draw it. Do you see that? you go from here, you go to here, right? But here is go to inside, you don't go to outside because this is inside. Then again, you don't see it because it's at the back of this ring. Then you will come to here. Do I draw it right? No. So you go from here. Let me see. And then you go to the back. Maybe I did not draw it right. Let me just Google and show you. Someone has a question?
Just a ring with like a single twist turn.
Exactly, the ring with a single twist. Thank you. Just hold on. Can you see it? So you will see that if I go from this point, right, A, it will go inside, you cannot see it, right? And then it will go the other side, B, and then go back to A. So basically, you need to go through 720 degrees in order to go back to the original point. Okay, so so it is more profound. It has something behind it related also to topology. But I just want you to remind you about this, because when you deal with spin in the future, not in this class, you will also find that you need to rotate 720 degrees in order to get back to the original state. Okay, I know this kind of disruption. I did not do this well. Any questions? Okay, if no, then let me continue, right? I only show you 360, but this should be easy. What if I do it 4 times? If I do it 4 times, of course, right, you can go through the math, but it is also very easy to see it directly. This is just equal to first do it 2 times here, and then apply to plus, right? So this one is equal to, because we already calculate 2 times, this is just equal to negative plus, right? This whole thing we did here already is just negative plus. Then we apply this to plus because it's linear. Then I get what? Negative times negative plus, which is equal to plus. Right? So it means that you need to do 4 pi. 4 pi is 720 degrees, right? So this is something you need to pay attention to. You usually don't need it, but sometimes it can get confused when we look at broad sphere. But here we'll just remind you that why you need 4 pi, right? You need 4 pi to go back to the original state. Now here I only show rotating about z axis. It is the same for any other axis. Okay? Good. Any questions? Okay. If no, then let's move forward. Now, so here I show you some common equation. You can try to memorize it or not. Yeah, it doesn't matter. I don't need you to know this in this class. But if you start working on more intensive quantum computing algorithm or look at the gate, you will start seeing this equation, right? Rotating about x-axis, you have sigma x on top. Maybe I start with z. We just done z, right? Rotating about z-axis, you have by theta divided by 2, okay? I mean by theta, sigma 2, sigma c, rotating by theta. I was using gamma so far, right? Gamma divided by 2. Here's theta divided by 2. It's actually equals to this matrix, okay? And similarly, you have x and y. And this is the matrix you will do to do the multiplication on the state that you want. Okay? Now I would like to talk about the matrix exponentiation. First of all, we need to understand the definition of matrix. Okay, but the first thing I need you to memorize is that any matrix to the power 0 is identity matrix. This is a definition. So what does it mean? Even you have A, B, C, D, take to the power 0 is equals to 1001. Okay, that is definition. Okay, so how do we exponential a matrix? Is by definition, right? Method 1, by it's exactly the same how we define exponential in Taylor expansion in a regular number. So it is that exponential a number alpha times the matrix equals to, you might have forgot, right? But now just take it for granted, summation n equal to 0 to infinity 1 over n factorial alpha m to the power n. I don't know if you remember this equation, but if you remember, e to the power x is just equal to summation n equal to 0 to infinity 1 over n factorial x to the power n. Right? If you forgot, try to take a look, check it. This is also the Taylor expansion. It's exactly the same. Here x is a real number or a complex number. Here m is a matrix. By definition, it is the same. Summation is an infinite sum. Each term weighted by 1 over n factorial, and then times alpha m to the power n. Right? So what does it mean? Now remember, we start with n equal to 0. Then when n equal to 0, m to the power 0 is what? By definition, it's just the identity matrix. Then we have n equal to 1, which is alpha m divided by 1 factorial. M equal to 2, alpha m squared divided by 2 factorial. And keep going to infinity. Right? And because alpha are just numbers, so this is just equal to alpha to the power 3 times m to the power 3. You just multiply the matrix 3 times. Okay, so that is the definition. So you can use this to evaluate any matrix. But of course, you need to calculate all the way to infinity. And this actually will make things more difficult, right? If you calculate all the way to infinity. Unless you can find some trend or analytical equation. Okay, but let's first look at case 1. Right? What if the matrix is diagonal? What if the matrix is diagonal? What does it mean? It means m equals to m0, 0, m1, 1, all the way to maybe some very big number, I don't write it, and then the rest is 0. Is this okay about why it's the meaning of diagonal matrix?
Yeah.
Okay, so good, thank you. So this is diagonal, right? Then let's follow the definition. Exponential alpha m is equals to summation n equals 0 to infinity 1 over n factorial alpha m to the power n, right? But let me spell this out. This alpha to the n, and then m0, 0, m11, m22. The rest is 0 to the power n. That is the definition. Now, the quick thing here is that this is a diagonal matrix. If you try to multiply a diagonal matrix to itself, because the rest is 0, right? You find that this is nothing but just just make this clear, equals to summation n equals 0, to infinity, 1 over n factorial alpha n. Diagonal matrix to the power n is just equal to its elements to the power n. Right? Try to do that. Try to do it numerically. You will see that, right? Because this row times this column is just m0 squared. This row times this column is just m11 squared. So this is just equal to this. So now you are just multiplying a number to this matrix and then add them together. And because of this, this is just equal to summation for each term, n equal to 0 to infinity, 1 over n factorial, alpha n, m00 to the power n. And then the second term is sum, 1 over n factorial, alpha n, m11 to the power n, and keep going. Right? Do you see that? Because this is just adding all of them. First, this is a number coefficient, so I can just multiply this to each of the term, right? That's why I get 1 over n factorial alpha to the power n, m00 to the power n, right? Same for other terms. And then it is just addition, right? So if I add this matrix together, it's the same as adding individual elements together. That's why I have this. Now this one is just the same as this, just the regular definition of a number, exponential, right? So this is just equal to exponential alpha m00, exponential alpha m11, exponential alpha m22, and then the rest is 0. Is this okay? Any questions? And based on this, I justify why I can just do exponentiation on the diagonal element when it is diagonal, right? So I don't need to worry about anything. I just do the exponentiation if it's diagonal. Any questions? Maybe my writing is difficult to read, so here I try to show you one more time, right? So for example, this is just a 2 by 2, right? E to the power this matrix. All you need to do is just use the definition, Taylor expansion, then you get this. When it is diagonal, it means I only have these two terms. These two are 0. Then of course, when you do this to the power n, you keep multiplying itself, you get this, right? And then this just go in, and eventually, in summary, when you exponentiate a diagonal matrix, you just need to exponentiate the diagonal element. Make sense? Okay, so that is good. Now the problem is, what if it is non-diagonal? Well, of course, you can just use Taylor expansion and just keep writing until infinity. For numerical calculation, you can do that. If it's not numerical, hopefully you can find a trend, right? Usually you can have to full trigonometry or whatever. You find that, there is, it converge to something, and then you can calculate. But this is not easy. So what we can do is that we first diagonalize the matrix. For M, remember, for every M, right, for this well-behaved one that we have been discussing, it has its eigenvectors. So we can diagonalize this matrix so that it becomes a diagonal form. When we say diagonalize, what do we mean? We mean express it in its eigenbasis. And you will see this in assignment 4. Right? For example, for sigma x, you express in the plus minus coordinate. If it is in plus minus coordinates, then it's diagonal, right? Then you can directly take its exponentiation because it's diagonal. But after that, transform it back to the previous coordinate system. Okay, so do you remember how to transform a matrix from the old system to the new system? It's very easy, right? We have this equation. U equals to the elements is the new coordinate I basis inner product with the old coordinate j basis for the ij element, right? That is the matrix that we use to transform from one coordinate to another coordinate, right? And again, this new is m's eigen basis. Okay, so I don't have example here. I want you to go back and work on the assignment. It's a little bit difficult, but not really difficult. It's just difficult in the sense that you need to understand, revisit what you learned before midterm about this transformation. And these are just the equation, and then you plug in, then you will be able to transform. Okay. Any questions from this high-level discussion? So I will say final. Stop here. Okay. In the next two classes, we're going to have presentation. I don't want to ask you to learn more new materials, right? But you need to know how to do the assignment. You don't need to work until here. In the next part of this class, I want to talk about error correction